This is a Pyramid model PS-21K regulated power supply. These are typically used to power CB radios, ham radios, things like that. It has a 13.8 volt output with a current rating of 20 amps. I believe it's a 20 amp surge, but only a 18 amp constant rating here. I was able to find some information on the internet on this supply. Got a little manual here that has some specs on it. You can look at this if you want to freeze it. You can see the specs on it if you have one of these. I was also able to find a schematic here. This is a pretty common topology for power supplies. This has been around for decades. One thing it uses the 723. This regulator chip has been around since the 1970s, so it's over 50 years old, and there are a lot better chips that are used in power supplies than this here. One thing in here, it says it's protected against overcurrent, and it will shut down if you exceed the current rating, which is great, but I don't see any protection on here against overvoltage. What I wanted to see was a crowbar circuit in the output, which I don't see. So if looking at the 4 2N3055 here, these are the pass transistors. If these short out, if even one of these shorts out, your full rectified voltage here is going to be connected through to your load here. One of the things I'm going to do, I'm going to measure the collector voltage here, see what the no load voltage is on the collector of these pass transistors, to see what an actual fault condition would be if you lose one or more of your pass transistors. Another thing I want to do is look into building a crowbar circuit that will trigger if the output voltage goes above, let's say 15 volts, it will short out the output and protect whatever you have connected to it there. I don't know the condition of this. It was pretty crusty. I cleaned it up. Here's your 4 pass transistors. I use the 2N3055. These are been around a long time also. I've got tons of these things, bins of them, so if these are bad, it'll be easy enough to replace. It's got a nice ammeter on the front, which is kind of nice. Here's your output terminals. I'm not so sure I'd want to put 18 to 20 amps through these connectors here, and I don't see any outputs on the back like some of the bigger Amtron supplies have. Also, it looks like this was modified, I believe, and here is looks like a, well, I don't know, I can't tell if that's a switch or an adjustment on it. Looks like it's a broken switch. I don't know what that is. I'll have to check that out. Anyway, I'm going to, before I power this up, I'm going to remove the enclosure and do an inspection of it, and then I think I'll put it on a dim bulb or a variac and bring it up slow. This thing was really cheap, and the guy, he didn't know if it works or not, so being a hamfest, I assume it doesn't work, and we'll go from there. So I'm going to open it up, and then we'll inspect the innards here next. 4 screws on the top, 4 screws on each of the sides, and the top comes off, exposing the inside, which it looks like it's been inhabited here. Yeah, I gotta clean this up. It almost looks like it needs a bath. Nice big power transformer. It's got a fan, which is good. Yeah, there's a toggle switch on the front here, a single pole single throw switch here with a broken handle on it. That looks like that was added, pretty sure. And I have a feeling that it goes to the fan. So evidently they put a switch on it to control the fan. I think better than that would be to put a thermistor and have the fan come on automatically if the temperature rises above a certain point. So that would be a good idea. Anyway, before I even get involved in this thing, I need to clean this up. It's in pretty bad shape. So I'll clean it up and then come back. Stand by for that. Well, I've cleaned the inside out. Looks a little bit better. Still kind of crusty, but there's no more spider webs, etc. So I think it's time to see if we can let the smoke out, if there's any to be let out. So what I've done, I've got a voltmeter connected up, and I have a dim bulb tester hooked up, and I'm limiting the current. Let's see, I have a 60 watt bulb in here, so that should limit the current to about 1/2 amp if I've got a direct short. So let's watch the bulb as I power it on. Well, it doesn't look like there's a direct short. The fan's running. I don't see any output yet, so let me hit it straight through. And there is the unit running straight through, and we have no output, which doesn't surprise me. So the next step will be to do some troubleshooting. Luckily I have a schematic, so that'll be some of our next steps. Stand by. Here are the 4 output transistors right here. And here are the 4 output transistors in person here. Although I don't think the problem with this unit is the outputs based on the symptoms I got when I first powered it up, I did want to check out each of the transistors. So what I did, and this is fairly easy, I disconnected the base and emitter from each 23055, left the collectors, that's okay. Anyway, I wanted to measure each one, measure the beta and the forward voltage here, and I marked each lead here. The blue and yellow are the 2 leads for the base and emitters, so I can get them back in the right place. But anyway, here's what I get for beta on each of the transistors, and they vary. One of them's quite a bit lower, not too bad. But anyway, here's the first transistor. The forward voltage here, they're pretty close. 575, 576, 577, 576. The betas, 2 of them are the same, the first and last. This one is a little lower on transistor number 2, this one right here. But I don't think it's going to matter much, so I don't think we're going to have too much of a problem here. If I had blown output transistors here, I would have put 4 of them on the curve tracer and matched them a little closer, but this is pretty good. So my suspect here is not the output transistors. I'm thinking it's the 723. Based on my experience, this is acting like the 723 regulator is bad. So we'll have to check and see here. Although there is, the 723, like I say, these things have been around forever. And the output pin here drives tip 41C. This is a driver to drive all 4 outputs because the 723 could not supply the drive current for 4 23055s. So that could also be the problem here. But I'll test that next. My experience is these things can give you problems. Anyway, I'm going to replace the leads, the base and emitters on the 4 outputs, and then I'm going to move forward with some more tests. So stand by. I'm going to measure pin 10 on the 723. This is the output that drives the tip 41C, drives the driver transistor that drives the 4 output transistors. Let's see if we get any voltage there. If that's not there, then I'm pretty sure that chip is bad here. So I'm going to power the unit on. Fan's coming up. Okay, I'm going to measure without shorting anything out, hopefully. Here's pin 10. And I'm getting, well, it's kind of drifting. I'm getting basically nothing. So the 723 is bad, so I'm going to replace that chip and then we'll see what happens. Stand by for that. The 723 regulator chip has been replaced. I'm going to apply power. Let's see if we get any output voltage here. And we do, 13.7. Okay, but that doesn't mean it's going to supply the load. It probably will. What I'm going to do next is I'm going to put the heatsink back on the unit here, and then we'll hook a load up and load the supply and monitor the voltage and see what happens. I feel better knowing that I actually tested each of these paralleled transistors. This was 4 2N3055s in parallel, so you can get one that opens and then the other 3 are going to you know, carry the load themselves. So I know they're all good, so that's good to know that. Anyway, I'm going to put it back together and then we'll put a load on it and see if it will supply the current. I have a old headlight as a load, and I'm going to start it up and let's see if we get any. And I'm also monitoring the output voltage here. 13.7, that's good. .4 amps. Let's connect another. There's the brights, and our voltage is staying up there at 13.7, and the transistors are just slightly warm. So I believe that's working. Let's see what the ammeter says. About 2.5 amps. That's about right. Okay. So the load test works, although we could add quite a bit more. I'd have to add some more. I've got some more of these lights I could add, or I got some big load resistors I can probably use too. So we'll try that. Load it up to, well, we'll load it up to about 15 amps. If it works, then I'll be satisfied. Now that this power supply is working, before I put it back together, I want to add an additional safeguard, and that would be a crowbar circuit. Now the output here, 13.8 volts, between that and ground, this is where you connect your expensive radio. And of course, if even one of these pass transistor shorts, it dumps 25 volts. There's 25 volts on the collectors of these. If this shorts from collector to emitter, you got 25 volts on your output, and that could do really bad things for your expensive radio. So what I intend to do, I'm going to put together a crowbar circuit with an SCR that will be across the output, so that if these do short, that SCR will trigger and it will short this to ground and save the expensive radio. I just as soon sacrifice this. This was a $5 non-working power supply from a Hamfest. If I connect a expensive transceiver on the output of this, I'd rather see this go up in smoke than the transceiver. Plus these are a lot easier to fix too. So what I plan on doing is this. SCR circuits, crowbars, are fairly simple devices here. I'm going to use an SCR. This is a big one I got out of a piece of equipment, and this heat sink is also salvaged out of a piece of equipment. So I'm going to take that, and this is just the basic circuit here. Have a fuse, and that will go across to the output here. This is plus 13.8 volts. And this would be the output of the Pyramid power supply here. What I will do this SCR here will be triggered from an overvoltage, and to do that I'm going to put a zener here. I think I'll use a, oh, I got some 15 volts here. These are let's see, 15 volt 1.5 watt zeners. So I'll have a zener diode here, the SCR here, and then a resistor here to limit the zener current. And what will happen is, if this output stays at 13.8 volts, this will basically be invisible to the output. But if we get a failure and it dumps 25 volts onto the output line here, this zener diode will conduct, and that will supply a gate current to the SCR. That'll fire the SCR, and that'll short the output, and that will protect the transceiver. So what I'm going to do is I will use a piece of perf board, and I'll mount this on it like so, and then the zener diode and the resistor, of course, will be mounted. Use some of these holes. I don't know, I'll probably use about maybe 100 ohm resistor, anything just to limit the current. So when this fires the zener, it'll limit the zener current. All you want to do is this to conduct, and then supply the gate drive to the SCR. Anyway, I'm going to build this circuit up, and I'll test it, and then once we get it perfected, we'll add it to the power supply. One other thing I'm going to do also, I'm going to add a couple of caps here, maybe one here and maybe one here. I'm thinking like 0.1 microfarads, and those will help if you get some transients in here. You don't want this to fire prematurely. If you get a transient spike in here, you want this to react quickly, so you don't want to get these caps too big, but you don't want it to prematurely fire on a transient that comes through here. So that's why I'll add two, like I say, probably 0.1 microfarad caps on there. So anyway, I'm going to build this circuit up next, and then we'll test that out, and that will be next. Stand by. Looking through my junk box, I found a large SCR. This is a C234. It's an old GE silicon control rectifier, and the anode is this side, the cathode is this big pin, and the gate is the small pin with the yellow lead on it. And in case you want to test one of these, what you do, connect a source through, positive to the anode, negative to the cathode, and then momentarily connect the gate to the positive lead, and then it should conduct. And here I'll show you here, I've got a supply limited to, I don't know, maybe a couple hundred milliamps at 20-30 volts, and I'm going to touch the anode to the gate, and you should see the meter measure current. I've got it on current right now. If you watch the meter, it'll measure current because it's going to conduct. And there you can see it's conducting, and it'll stay conducting even if I remove the gate terminal, which I'll do now. And you can see it's still conducting current. So this SCR is good. So I'll use this one in my Crowbar. And this one is good for 25 amps continuous and a surge of 250 amps. So this will have no problem shorting out the output of that supply if I have failure of the pass elements. Anyway, silicon control rectifiers. Great device. Here's a completed Crowbar circuit here. Here's the SCR, and then I've got the divider, which is it goes from the Zener cathode, the anode through a resistor, and then up to the gate of the SCR. And then I've got a negative lead from the cathode of the SCR that goes out to the negative lead. And the positive or anode of the SCR is connected here, and that goes out. Again, here is the schematic here. Pretty simple circuit. 2.1 microfarad caps. One from the positive to ground and the other one from the gate to ground. And right now I have a bench power supply here, and I have the current limited, so what I'm going to do is I'm going to slowly bring up the voltage on this supply, and when the SCR fires, the voltage will drop down. So I'm going to monitor the voltage across the SCR, or the black and red lead, and watch the voltage. So now I'm going to bring it up slowly. There's 4 volts, 5 volts, 6, 7, 8, 9, 10, 11, 12. Okay, 13.8 is what this is supplies rated at, so it'll run along at 13.8 volts. And now I'm going to bring it up. It should fire at around 15. So I'm going to bring it up a little bit more here. There's 14, 14.8, 15. Well, it's over 50. Up there, whoop, there it goes. Dropped down to 1. And as you can see on the meter here, the current is 0. So now I'm going to disconnect the voltage, run it back down, plug it back in, and we should be able to run the voltage back up to 13.8. And it's a little over 15 volts till it fires, but I think that should be okay. I don't want transients to trigger this thing, and the 2 capacitors should help alleviate that problem. And this should run along fine at 13, but once we hit over 15 volts, this SCR will fire, and this SCR, as I say, will pass 25 amps continuous and a surge of 250 amps. So that should short these 2 wires out, and that will protect your expensive transceiver. So now I'm going to mount this circuit in the Pyramid power supply, and then we'll give it one final test, and then we'll put the lid back on it. So stand by for that. Here's the completed Crowbar circuit. I've got it mounted on a standoff here. It's insulated. It's connected across the output terminals. And I also replaced the fan switch here that was broken. Of course, the original did not have a switch for the fan. I guess they wanted to run all the time. Although if you have a small load on it, it really isn't necessary. You know, if you're only running a few amps, it shouldn't be a problem. And the fan, at least this fan, is mainly blowing on the transformer here. But anyway, I'll turn it on. And I got the fan switch. Run the fan. So it seems to be working alright. Ammeter's working. Here's a schematic of the Pyramid PS-21K power supply here. It's kind of interesting. When I first looked at this, I thought, what in the heck were they thinking? It's, you know, if you look at the power transformer, first of all, it looks like when they drew it, they shorted out the windings. These points here should be erased. Maybe they drew a, I don't know why they drew it that way. But anyway, these points are not connected, of course. It would short the transformer out. And then the first thing that caught my eye was they're only using part of the main bridge rectifier here. This is the large bridge on the unit. And instead of using it as a full bridge, they're using it as a full wave center tap here. So the center tap here is grounded, and then if you look at the two sides here, here's your positive, here's your positive, which feeds this rail, which is the main rail that feeds your 4 pass transistors, and of course then their emitters are connected together through the ammeter to the output. Now there's another bridge here that's set up, and it's got a secondary winding here that feeds that, and that provides the supply voltage for the 723 and the driver here, the tip 41C. The tip 41C drives the 4 parallel connected pass transistors, the 2N3055s here. Now the 723, this chip has been around forever. I mean, I think it came out in like 1968 or 69, and there are a lot better chips available to do this function, but this was so good it's even used today. It's pretty amazing. I think Astron still uses them at some of their supplies. I'm not sure if the newer ones have gone to something different. But anyway, this pretty amazing chip here. It's kind of like the 555. It just doesn't want to die. And looking at this, how this thing works here, if you look at pin 6 and pin 7 across here, this is a Zener reference voltage. This is generated inside the chip. You've got a Zener diode that's fed with a constant current source from a FET. So at pin 6 here, this is a constant about 7 point something volts here. And in this case, they're connecting that directly to pin 5. Now this op amp is used as a comparator, and the top pin 5 is connected here directly to the positive input of the comparator here, and that compares pin 4. This is the negative input of the comparator, and if you look at where that's connected over here to a series connected resistors here at this point, and this is your voltage reference to sample the output voltage, and that's fed back into pin 4. So what happens is pin 5 is a constant, pin 4 varies with the voltage across this divider, so that's how we keep our voltage constant here. The output of that op amp here, this comparator, drives the output transistor of the 723, and that transistor directly drives the buffer. The tip 41 drives the parallel connected output transistors. So that's where you get your voltage regulation. The 723 can also provide a current limit, and it does that through these two pins, 2 and 3. Pin 3 is a current sense, and if you look here, that's connected right over here directly to the output. And you have the current limit, which is on pin 2, that's connected over here to the top of this resistor to ground, which is in the emitter of the driver transistor. So the way this works is if the voltage between 2 and 3, if pin 2 becomes more positive than pin 3 by more than 0.6 volts, this transistor conducts and pulls drive away from the output transistor in the IC, and that decreases your output, which comes in through pin 11. Your output current will go down. There's not enough drive. So what they're doing in this case, it's kind of interesting. They're measuring this point here, which is the output voltage. So in a high current condition, the output voltage will begin to decay and go down. But pin 2, which is fed from the emitter of Q1, this is in a separate supply from the main supply here. So eventually, under a high current condition, point 2 will get higher than pin 3, and that will cut your gain down. Now I did a little interesting test here. I measured the voltage of pin 2 and 3 under various conditions. First condition was under no load, and under that condition pin 2 measured 0 and pin 3 measured 13.8, the output of the supply. So then I put a load on it. I put about a 2.5 amp load on it, and at that point pin 2 measured 13.138 volts and pin 3 measured 13.76 volts. So you can see pin 3 is starting to come down and pin 2 is starting to come up. And as I increase the load further, pin 2 would slowly come up as pin 3 dropped. Now as you get to the point where the current loads the supply down, where the voltage decays at a too low of a point here, pin 2 is higher than pin 3, turns on this transistor here, pulls your gain away and shuts it down. So it limits the current here. If you shorted the output, this would limit the current and keep it from going sky high and blowing up your output transistors here. So at the same time, under a high load condition, if this output decays down to a certain point, if you look up here, this resistor is connected to the output here through this resistor R12, and that drives Q2. So if the current goes up enough where it pulls the output down, that would turn off Q2. Q2 is right across this LED, and that would cause this LED to light up. It's fed here. That's assuming you have enough voltage available still from the output of the bridge rectifier here to drive the LED. So in this power supply, the regulator is regulating the voltage, and it's limiting the current. If it gets too high above the rated current, it will full back the current. But if you look at it, it's not protecting the output against a shorted condition. If one of these pass transistors shorts, it's connecting the collector to the emitter. Now I measured here at this point here, this measures 25 volts DC. So a short of any one or all of these transistors will dump 25 volts across your load, and your expensive radio may go up in smoke or be damaged. So that's one of the things about the supply I didn't like. So in my case, what I did, I built a crowbar circuit that's connecting directly across the output to ground. So in the event one of these or all of these pass transistors short, that SCR crowbar will fire and take this point to ground, and then hopefully it'll blow the fuse. I should probably add a fuse somewhere up in here that would blow maybe at 20 amps, but this is a cheap supply I picked up, and I would rather sacrifice this supply than an expensive transceiver. So as long as I can pull this point to ground, that's the main thing. So if you have a supply like this that doesn't have a crowbar in the output, I suggest you build a crowbar circuit. They're fairly simple and may save your expensive radio. Something else I found interesting, this temperature switch here, it's a thermostatic switch, isn't on the heatsink with the output transistors. It's actually connected next to the transformer, which I would have thought, you want to monitor the temperature of the output transistors if it gets too hot. But anyway, that's the way they designed it. That completes this project. I'll put the top back on, and I'm going to put an insulator over the anode of this SCR to the case will clear it, but it's kind of close, so I'll put some kind of a small mylar insulator over it or something. Anyway, that concludes this project, so I hope you enjoyed it, and thanks for watching, and we'll see you in the next one. Bye for now.